All right, class, here is section 1.6, transformations of functions. So the idea of this section is how do we create new functions out of our basic or toolkit functions were discussed in 1.3. So in other words, just to take it a little bit on the side, we already have graphed or know what the function x, f of x equals to x. What happens if you have x plus 3 or maybe x minus 5? So how will the graphs of these functions be obtained from the basic function of f of x equals to x? The same thing could go to the square root of x function. What happens if you have a square root of x minus 5, right? Or plus 2, or the minus is inside the square root. So these are the graphs of these functions are going to be very similar to each other, but how are they different, or how do we obtain one from the other? That's the idea here. So the first thing is about vertical shifts. So given a function f of x, a new function, say g of x, maybe call it g of x, is the f of x plus c. So what happens if you add a number to your function? What does that do to the graph of it? Now it says if you add a positive value, the graph will shift up. If you add a negative value, in other words, you subtract, the graph will shift down. So here is a function f of x, which, by the way, if you look back at your notes in 1.3, that very much looks like the cube root function. Yes. So, in other words, what would the graph of the cube root of x plus 1 look like? So you add 1 to the function. It's really easy. All we're doing is just shifting the graph up, because all the y values you had before, remember, when you plug in an x, you create a y value. All the y values you had before are going to now be 1 more. So you're just adding 1 to the y values. Therefore, your whole graph goes 1 unit up. Okay, so I hope that makes sense. All right. Now, what would, for example, an f of x minus 2 look like? So in other words, what would a cube root of x minus 2 look like? I'm going to take all these points and move them 2 units down. Okay, so that's that shift. So in other words, again, if I needed to graph the cube root of x minus 2 function, that's how I'd get its graph. Simply shift our basic cube root function down 2 units. So let's practice on this idea some more. So let's say this is some function f of x, which, as you see, is a quadratic function, is an x squared function based on its graph. It's not our basic x squared function. It's already been shifted. But here it is. How would I, for example, obtain f of x plus 2? How do I get the graph of that? Well, again, that simply means to all the y values you had before, you add 2. The y values you had before, you add 2. Now, we do not change the x's, right? So the change here is in the y values only, right? So f of x is our y's. This is now y plus 2. So all our y's are moved up 2 units, I'm sorry. So the graph is just simply going to shift 2 units up. Now, what would f of x minus 3, for example, look like? So again, it's all the y values you had before. This y is a 1. Minus 3 is now going to go down to negative 2. So again, your graph looks just like it did before, is just going to move down 3 units. And by the way, that's the same thing as adding a -3. So this is why I'm saying if you add a positive value, the graph goes up. If you add a negative value, in other words, adding a -3 is the same thing as subtracting 3, then the graph moves down. Now, in a horizontal, so vertical shift means up and down the y-axis. Yes, so changes are made to the y. When you're looking at a horizontal shift, that simply means stuff is happening left and right. Therefore, the changes are made in the x values. So again, as you see, the change is made to the x's before you apply the function. Okay, so unfortunately, I know you're not going to like this, but that's actually how it works, that if you subtract something positive, if you subtract, you actually don't go left, but you go right. If you subtract a negative means you have a plus sign in there, you will go left. So let's see how that goes. So here it is. There's a function f of x, the graph of some random function f of x. By the way, it's our cube root function from before. Now, f of x plus 1, that simply means what? That simply means you are cube rooting not x, but x plus 1. So see how the difference is that you are changing the x values before you applied this cube rooting function, okay? So the plus 1 is inside versus the plus 1 was on the outside of the cube root before. So in other words, the changes are made to the x values. So I know that you'd be very tempted to see x plus 1 and you want to go 1 to the right on the x's, but it's the exact opposite and you're going to go 1 to the left. And it exactly works just as it is. So we moved the graph, we shifted the graph 1 unit left. So when you subtract the negative, that means a plus 1, you are going left. Okay. Now, if I wanted to graph, for example, the function f of x minus 2, so by the way, the graph of that would be, or the equation for us would be cube root of x minus 2. So again, contrary to what you would want to do and go left, you would go 2 units to the right. So the graph goes to the right, 2 units. Okay. And again, we can easily test this with actual points on a function and actually plot those points, and you see how indeed the graph goes the way we say. So if it says plus 1 on the x's, you go left. If it says minus 2 on the x's, then you go to the right 2 units. Okay. Well, I'll summarize this for you. But again, whenever it comes to x's, you will always do the opposite of what the operation says. So here it is. Let's say this is some kind of function y, some f of x or y, and then I would like to graph here. Let's say I would like to graph f of x minus 2. So what does that mean, f of x minus 2? Means to go 2 units to the, not minus, but to the right. So we're going to move all these points I had before 2 units to the right. So it's still the same shape, it just moved 2 units right. And let's say I would like to graph the function f of x plus 3. So the plus 3 simply means you go 3 units left in a negative direction. This is going to be a common theme throughout the semester, so you will get used to 1, 2, 3. So as you see, all I'm doing is just grabbing specific points and just as they are, shifting them 3 units left. Specific points, shifting them 3 units left. So counting and going left. Okay. So these are vertical versus horizontal shifts. So verticals, changes are made to the function, or in other words, to the y's. Horizontal, the changes are made to the x's. Okay. All right. So here it is. Let's just practice this right away. And here are my shifts. So I've given you a couple, I'm going to just use colors. So here's my basic function. F of x is the absolute value of x. And if you remember, the absolute value of x goes through all these corners, 1, 1, 2, 2, 3, 3. But then it's a v, and it goes through all these corners nicely on the left side. So this is the absolute value of x function. Okay. Now, what did the problem say? If I minus 2 from the x's, so it's the absolute value of x minus 2. So the change is made to the x values. So therefore, I have to go 2 units to the right. So I'm taking all my points, and I keep the shape exactly as it is, but I'm going to go 2 units to the right. So that's the absolute value of x minus 2. Okay. Let's try this next one. I'm also going to graph it on the I'm also going to graph it on the same coordinate system, x, the absolute value of x plus 3. So what's the difference here? Again, as you see, I'm adding 3 to the absolute value, so to the y's from before. So all the y's from before are now adding 3 units to them. So therefore, this graph is going to go 3 units up. So from before, I'm going to move all these points 3 units up. The shape is the same. It's still this V. So this is the absolute value of x plus 3. Okay. All right. So here I'm combining both. I have 2 operations. One is happening to the x's and one is happening to the y's. So I'm going to do one at a time. So I'm starting with my absolute value of x function. And there are 2 operations here. One is happening to the x's, the other one is happening to the y. You could do both at the same time, but we're going to go nice and slow. So the absolute value of x plus 1 means you're going to move 1 unit left. So x plus 1, you want to go right, but you're going to go left. It's the opposite always of what the operation says when it comes to x's. And then minus 2 means move this whole graph 2 units down. So the one that you got already, move it 2 units down. So here is our final answer. And as you see, this final answer is got both. So we moved 1 unit left from the origin and 2 units down. Okay, so 2 operations have been performed, 2 shifts. One that came from x values and one that came from the y values. All right. Now again, this is not just, it is an absolute value function, but not one that just says absolute value of x, right? So it's changed quite a bit. The shape of it is still the same, but it's on a different part of the xy plane, right? It just got shifted from its original place that went through 0, 0. Oops. Okay. All right, so let's look at another type of transformations. These are vertical stretches and compressions versus horizontal stretches and compressions. So let's see what that is. So given a function, a new function c times f of x. So you multiply something to your function, to your y values, is a vertical stretch or a vertical compression of your new function. So if you multiply by a number more than 1, let's say 1.5, 2, 2.3, 7, then the graph will be vertically stretched, so it becomes longer vertically, okay? If you multiply by a number between 0 and 1, and again, we already said c is positive, and between 0 and 1. So if I say between 0 and 1, that clearly is a positive. So if you multiply by a half, a third, a fifth, 2/3, 2/7, things like that, then the graph is going to be vertically compressed. So here is an example. So you're starting with the function, the blue one, f of x. That's its graph. Okay. Now what does 2 times f of x look like? It's twice as high. So you multiply the y values you had by 2. Now if you multiply, and we'll see this in a minute right here. So we multiply the y's by 2. That's exactly what it says. 2 times, remember, f of x stands for y. And what is 0.5 times f of x? Well, that's the same thing as 1/2 times f of x, right? 0.5 is a half. So you just simply take half of all the y values you had. So whatever y value you had here, I'm just going to cut it in half. So therefore you have a vertical compression. The graph gets squished in vertically. And it's again vertically because it happens to the y values. Okay. So let's take this function f of x here. What would 2 times f of x look like? Well, 2 times f of x, as I said, take all the y coordinates you have and multiply them by 2. So this y coordinate here is a 1. Now it's a 2. This y coordinate here is a 3. When you multiply by 2, it goes to 6 because that's what 3 times 2 is. This y coordinate here is a 2. Again, think only about the y's. The x's stay the same, so we're going up and down on the same vertical line. So this y coordinate is a 2. Now it's a 4. This one's a tricky one. This y coordinate is a 0. Yes? So 0 times 2 is still stays at 0. So it goes up, down, down. So this graph got stretched vertically by a factor of 2. What would 1/2 or 0.5 times f of x look like? Okay. So again, this y value was 1. Now it's a half. This y value was 3. Now is 1.5 or 3/2. This y value was a 2, divided by 2 is a 1. This y value is a 0, divided by 0 is still a 0. There you go. That's a vertical compression. Okay, the graph. So the graph got squished in vertically. Let's try with a specific function. So let's say I'm picking the function f of x. I'm taking one of our basic functions. Let's say x squared. So when you look back to your basic functions, that's what the x squared function is going to go through. 0, 0, because 0 squared is 0. 1 squared is 1. 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. So here is my x squared function. Okay. How will the graph of it compare to 3 times x squared? So as you see, I'm multiplying 3 to all the x squares I had before. So in other words, to the y values I had before. So all the y coordinates are going to get multiplied by 3. This y coordinate is a 0, so stay 0. This y coordinate is a 1. Now it's going to go to 3. This y coordinate is a 4. It's going to go to 12, is way up there. I can't even find it. But really what you notice is that the graph got stretched vertically, it became elongated, it became longer vertically by a factor of 3. So let's try 1/3 times x squared. So 1/3 times x squared, that means take all the y values from before and multiply them by 1/3. So 0 times 1/3 is still 0. 1 times 1/3 is 1/3. This is 4. 4 divided by 3 is 1 1/3. So as you see, the graph got squished, compressed vertically by a factor of 3. So it goes up 3 times as slow as before. Okay, so that's what a vertical compression looks like. All right. Okay. Now, of course, horizontal stretches and compressions simply means that stuff is horizontal. Again, means that stuff is happening to the x's. Vertical means that stuff is happening to the y's, right? So we took the whole function and the whole y's and multiply them by certain numbers. Okay. Now I'm taking the x's and multiplying them by numbers. Just the same as we did with the horizontal shifts. So that means stuff is happening to x's. And of course, as I said before, when stuff is happening to the x's, you do exactly the opposite of what the operation says. I'll summarize it for you in a minute. So here it is. If I start with the x squared function, kind of like the one we just did, well, where is the change happening? The change is happening to the x's before we are using the squaring function. So see the difference in the equation here? I multiply the whole x squared by 3. Here, I'm multiplying the x's by 2, and then I'm using the squaring function. So the order matters. Again, it's a change to the x's and not to, and then we're applying the squaring function, right? Then we're finding our y's. So, of course, exactly as I said, it's just the opposite. So instead of multiplying the x's by 2, I'm dividing the x's by 2. So whatever x value I had, I'm now taking half of it. So it's a horizontal compression. And if I multiply the x's by a number between 0 and 1, in other words, a half and so on, then I do exactly the opposite. So instead of dividing by 2, I multiply the x's by 2. Okay, so the graph gets horizontally stretched. Okay, so let's practice on this. So let's say the blue is some kind of function f of x. How do I get f of 2 times x out of it? So 2 times x simply means to divide all x coordinates by 2. So it's the opposite. Same as when it's at x minus 1, you added 1 to the x's. It's at x plus 2, we went left and we minused 2. So here is the x coordinate of this point is 0. Dividing it by 2, it still says a 0. The x coordinate of this point is 3. Dividing it by 2 is a half. See how I'm not changing the y's? I'm not changing the heights. I'm just changing the x coordinates. Okay. This x coordinate here is a 6. When I divide it by 2 is a 3. It's at the same height. I'm not changing the y's. I'm changing the x's this time. And finally, the last point here I'm going to hold on to is a 7. Half of 7 is 3.5 at the same height. So what we got is a horizontal compression by a factor of 2. So the graph got squished in horizontally by a factor of 2. Okay. The y's stayed the same. I never messed with the y's or the heights. And what would 1/2 times x do? Okay, so again, the changes to the x's. So instead of dividing all x's by 2, we're going to multiply all x coordinates by 2. Okay, so just the opposite. Here it is. This x was 0, stays a 0. This x here is a 3, right? It's now going to move to 6. That's going to be tough. This x here is a 6, is going to move to 12. That's about where 12 might be. And then this x here is a 7. So it's going to go to about 14. So I know I'm getting off this graph, but it's up here. That's why I couldn't find it. And this x is here at 6. Don't mess with the y's. So this point moved to the right. This point moved far right. And then far right. So as you see, what happened to our graph is that it got stretched horizontally by a factor of 2. Now, really, just to summarize it, I did write it down, but I don't want to keep... Where did it go? So when you think about the horizontal transformations, you have to always think about it's the opposite. So what you always think is, what would you need to do to solve for x, to get x by itself? So that's really the trick of figuring out what the changes are. So when there's a change to the x and you want to get x by itself, what would you do? To get x by itself here, you would add 2. So therefore the graph, you add 2 to all x's. If, again, same thing here. There's an x transformation. To get x by itself, what would you do? You divide by 2. So therefore you divide all x coordinates by 2. Same thing here. You want to get rid of the 1/2 that's multiplied to x, you multiply by 2 to get rid of the 1/2. So therefore you multiply all x's by 2. So always think about what would you have to do to solve for x. So let's take one of our basic functions. For example, I'm going to take the absolute value. So that's another one we know how to graph. and I'm going to perform some x transformations to it. For example, again, what does it mean an x transformation? It happened inside right next to x before we applied the absolute value function. So 2x means take all the x's and divide them by 2. Take all the x's and divide them by 2. So bring the points halfway in. The heights do not change for all these coordinates. I'm just dividing all the x coordinates by 2. So it resulted in a horizontal compression. So the graph got squished in horizontally. If I have 1/3 x, then I'm multiplying all the x values by 3. So here it is in green. This x value is a 0. This x value is a 1. I'm going to multiply by 3, so I'm going to move it to 3. This x value is a 2 times 3 is going to go to 6. So this graph is stretching horizontally by a factor of 3. So it's 3 times as wide as the original graph used to be. So let's play with this function here and let's see if we can do some transformation. So let's say this blue half circle here is some kind of function f of x. Okay. And I'm going to do both of them right now. I'm going to look at both x and y transformation. So how would I graph 2 times f of x? Now 2 times f of x means multiply all y's by 2. It's a transformation to the y values because it's multiplied to f of x, so to y. So this is a y of 0, so it stays 0. This is a y of 2 times 2 is 4. This is a y of 0, so it stays 0. So as you see, what happened, the graph gets stretched vertically by a factor of 2. What would be f of 2 times x? So what's the change here? The change is to the x values, and when it comes to it, you do the opposite. So don't multiply by 2, but divide all x's by 2. So this x coordinate of this original point is -2. When I divide it by 2, it becomes a -1. The x coordinate of this point is 0. When I divide it by 2, it stays a 0. The x coordinate of this point is a 2. When I divide it by 2 is a 1. So here it is. The graph got compressed horizontally by a factor of 2. Okay, so these are basic transformations. Again, practice is going to make things better. So, all right, reflections is our last transformation, and it's about multiplying by negative numbers. So if you think here, I kept the c values, the values I multiplied both horizontally or vertically, to positive numbers. Now, what if we multiply by a negative? So in other words, what happens when you put a negative in front of the f of x's? Well, that's pretty straightforward because all your positive x's are now, all your positive y's are now becoming negative y's. So you just simply get a vertical reflection, or in other words, a reflection over the x-axis, right? So all your positive y's are now negative y's. And if you put the minus to the x's, right, then all your positive x's are now negative x's. So that's just simply a reflection over the y-axis, right? So you make all your positive x's now negative x's and backwards. So it's a horizontal reflection, in other words, a reflection over the y-axis. Okay. So let me give you some kind of, let's start with the square root function. Okay. What would it look like if I now graph negative square root of x? So let me graph for you the original square root function, which is like our parabola sideways. Remember, the square root function goes only to the right of 0. Okay. Now a negative all of it, so you simply reflect this over the x-axis. So all your, oops, I went too wide, I believe. All your positive y's are now negative y's. There you go. So all your positive y's are now negative y's. Now if I do the same thing to the square root function, but I put the minus inside, then it's going to be a reflection over the y-axis. So all the x's you had before are now opposite. Okay. So it's a reflection over the y-axis into negative x's. Now remember, you might be like, wait a minute, I thought I can't have negative numbers inside the square root. No, you can't. But what kind of values I put in here to the green one? So as you see, I'm plugging in a -1. So what does the extra minus do to this -1? It makes it back a positive, so it can work. So yes, if your x's are negative, then you better make them back positive by putting an extra negative symbol in front of them. And then yes, square root of 1 is 1. If I have a -4 to plug in, that's why I have the extra minus. Minus minus 4 is +4. The square root of it is going to be 2. So again, just because you see a minus in front of an x, it doesn't mean we're dealing with negative numbers. X could be any number, is a variable. It stands in for an unknown quantity. If these unknown quantities are negative, then we better make them back positive so we can have them inside a square root, right? So I get that question a lot in class, so I know you probably had it as well. All right. So here it is. Putting it all together, vertical versus horizontal transformations. What if you're dealing with multiple transformations? How do you perform them? Well, vertical versus horizontal transformations can be done independently of each other. So you can take care of all vertical transformations, then all horizontal transformations, one of each, and it gets confusing. I personally like to start with all the things that happen to x. So I always like to start with all the x transformations and then take care of all the y transformations. If you have multiple y transformations, they have to be performed in the order of operations. Okay, so again, I'm not going to give you too complicated of functions, maybe one thing at a time, two things at a time, but really not more on a test. But if you must perform multiple vertical transformations, so stretches, shifting, which one do you do first? It's the order of operations, right? So in other words, all multiplications, which is stretches or compressions, and then all additions or subtractions, so vertical shifts. Of course, as it's been happening this whole section, horizontal transformations are going to be performed in the reverse order. So you have to think about what you would do to solve for x. So let's say here are two x transformations, yes? So again, what I'm saying is think about what you would do to get x by itself if it was an equation and you wanted to solve for x. So what's the first thing to do to get to x? You minus 1, yes? You get rid of the 1. So see how you're not adding 1, you're not going to the right, you're going the opposite way. You're going to go left, yes? That's why you go in the opposite order. Then what else do you do to get to x? You don't multiply 2 again, you divide by 2. So that would be exactly in the reverse order of operations. So you minus the 1, then divide by 2, and then your x is cleaned up. So that's how you have to think of it. Okay. All right, so it says just describe the transformations needed to graph these functions. So I'm going to start with this one because there's only two things. So it's some kind of random function, f of x, that you switch to an f of x minus 1 and then plus 3. So because of the x minus 1, you're going to shift the graph 1 unit to the right. So minus means plus 1, so you go to the right. And because the plus 3 added to the function, you're going to shift the whole graph 3 units up. Now, the order doesn't matter. You can go 3 units up and 1 to the right, or you can go 1 to the right and 3 units up. You end up in the same spot. So that order didn't matter. Here there are a couple things, and then this is why I'd like to see how I have the minus 1, the multiplying by a negative, and then the adding the 7. So there's 3 things going on here. I also always like to start with the transformations to the x. So start with the x transformation. So before we even cube the function, so we're really dealing with the x cubed function. But this is how this was the x cubed function, if you remember. What are the transformations? How do we get from the basic x cubed function to this function here? First of all, we shift the whole graph 1 unit right because the x minus 1. So you shift the whole graph 1 unit to the right. The second thing, see how there's a multiplication by a negative 1 and an addition by 7? These are the 2 transformations to the function. Well, we're going to do the minus first. So second of all, because of the minus, reflect the graph. All your y values become negative y values. So reflect the graph about the x-axis. So all your y's are now negative y's. And finally, the plus 7 to the function simply means that we're going to shift the graph 7 units up. Okay. You can write units or you can just not write them. Just save some time. Okay. So here are just a couple graphs for us to graph using transformations. Now, I'm going to write them step by step. So the first thing you're going to do is look at what function you're starting with. And this is the x squared function. So here is the x squared function. Okay. Then there's 2 transformations, one that happened to the x's, and because of the x minus 3, that means you move the graph 3 units to the right. Okay. And because of the plus 1, then you further move this whole graph 1 unit up. And this is our answer in the end. Okay. Here it is. We're going to start with our basic function, which is the absolute value function. So it's the v. And then I have a couple transformations. One that's to the x. So I'm multiplying all the y values, all the x values by 2. That simply means divide all the x values by 2. So squish the graph in horizontally by a factor of 2. And finally, I have to take this absolute value of 2x minus 1. So the minus 1 happens to the y values. They happen to the absolute value function. So it's shift all the y values you have from the red one. I'm now moving all those points 1 unit down. So move all the points further 1 unit down. Not the original one, yes. So 1 by 1. So the graph got squished by a factor of 2 horizontally and moved 1 unit down. So this is the final answer, the green one. All right. 2 transformations here as well. So as I said, that's kind of all I'm going to put for you on a test. I believe in the homework as well. So number 1. Start with the square root function. This is our basic function here. I'm holding on to a few points. It always helps to bubble in certain points because then you think about their x coordinate and their y coordinates. The next thing I'm going to do, I always like to start with the x transformation. So this minus x just simply flips the graph over the y-axis as we just did before. And the final answer is to take that new graph you got and add 2 to it. So move these points 2 units up. So it's the square root function as you see. They got moved 2 units up and reflected over the x-axis. It would be in the same place if you started with a plus 2 to the y's and then reflect because of the x's that were now negative. Again, you can try this yourself. I'm going to start again with the square root function. It goes to 0, 0, 1, 1. The square root of 4 is 2. So these are the points I'm bubbling in. I always go to x transformations first. So the 2 times x makes the x's get squished in by a factor of 2. So I've divided all x coordinates by 2. You can think of it as an extra transformation. See how now I have a y equals to -3 times the square root of 2x. So you can think of it 2 ways, or you can think of it together. So you multiply all the y values by -3. By multiplying it by a -3, the negative first makes all the y's become negative. And then the extra 3 makes them 3 times as much. So you could, from beginning, multiply by a -3. So this y was at 1, now it's at -3. This y is at 2, now it's at -6. So there you have it. It's flipped because of the negative, and it's 3 times as wide as it was before. So here is your y equals to -3 times the square root of 2x. So it gets compressed horizontally by a factor of 2, so it got squished in twice, and then stretched vertically by a factor of 3. And because it was minus, it also got flipped over the x-axis. So all the positive y's you had before are now negative y's. All right. Let's try this one more time. Write a formula for the function that results when the given toolkit function is transformed as described. So we are starting with the x squared function. This one's reflected over the x-axis. Over the x-axis simply means to put a minus to the x squared. So put a minus to the x squared. All your y's become now negative. And then vertically compressed by a half. So that means vertically means we multiply all the y's by a half. So it's just simply compressed into half as high as it used to be. That's it. Now we're starting with the cube root function with it, and it got shifted left, so it went left 3 units. That means I have to add 3 to the x's. So instead of going to the right, as we would think, because as x plus 3 is, again, you minus 3 from all the x's, that's why you go left. And then 4 units up, that means we're adding 4 to the function, so on the outside, and we're just adding 4, as it says. And I know this is a long section, but we're almost done. And we also will be done with chapter 1 as soon as we're done with this. And so it's all about even and odd functions. Now, with all these reflections, some you see and sometimes you don't quite get to see. And the last thing to discuss about functions in this chapter is which functions are even and which functions are odd. So a function is called even if you plug in negative x's for x's, the function stays the same. So let me give you a very good example of an even function. The x squared function is an even function. So you could also look back at your library of functions and what functions are even. The x squared function, it looks the same. When you plug in a negative for x, you get the same answer. So these kind of functions are symmetrical about the y-axis. Another good even function is the absolute value function. Its graph, plug in a negative x for x, you get the same thing. So the graph is symmetrical about the y-axis. Odd functions, it's the exact opposite. As you plug in a negative x for x, you get the opposite. So a good example of an odd function is the cubing function, the cube root function, and there you see why such functions are even versus odd. These are called even because the x squared, which 2 is an even number, looks like that. Odd functions like x cubed, which is an odd number, is an odd function. Their graphs are symmetrical about the origin. Okay. To decide if a function is even or odd, what we simply have to do, if we don't know how to graph it just yet, which we don't, is plug in a negative x for x and see what happens. Well, when you plug the negative in here, you'll get still the same. A negative times a negative is a positive, and then plus 1. So if I compare this function to the original one, Is it exactly the same? No. So it's not an even function. Is it the exact opposite? So all signs have changed. No. So it's not odd either. So this one would definitely be neither. And really the quick trick for it is that you see that you are mixing what? Both even and odd exponents. So it's not all even and it's not all odd. Okay, therefore it's neither. When you look at this next example, already you can tell that I'm only giving you even exponents. So when I plug in negative x for x, a negative to the fourth power is a positive. Same thing, a negative to a second power is a positive. And the 5 is 5, and by the way, is a power of 0 for x. And when you look at it, it's exactly the same as your original function. Which means, when it's exactly the same as the original function, this is an even function. Its graph, when I'm going to graph it, will be symmetrical about the y-axis. And here is the last one. And what do you notice about this function here? You notice that I'm only giving you odd powers. 1/3 would be the same as the power of 3. So the cube root of 3 negatives is a negative. A negative raised to the 5th power is a negative. So when I compare this expression to the original function, I see that all the signs have changed. So I'm getting the exact opposite of what I had started with. Okay, which makes this function an odd, and its graph will be symmetrical about the origin. Okay, and that concludes our chapter on functions, period. Okay.